CTA. Another thing that is crucial when we are observing the extragalactic sky in the very high energy gamma rays is the sensitivity in the lowest time bins, because this phenomenology is all of it is either very variable, which is the case of blazars, or simply very transient, so it exists there only for a couple of minutes. So the sensitivity in the short time scales is crucial for all extragalactic science cases. I will now move on to describe some details of the active galactic nuclei key science program that we wish to perform with CTA. It will have 3 different observational strategies, and it will also address many different science questions. I will focus on the AGN physics questions at very high energy gamma rays in this talk, because that's my own field of research. But the AGN key science program will actually address also the question of gamma ray cosmology, so I will touch upon that, and is also very relevant for ultra high energy cosmic rays and fundamental physics question. It consists of 3 different observational strategies, like I mentioned. So there is a program on long-term monitoring and of a small sample of AGNs. I will then tell why that is relevant. There is a program on high-quality spectra, and then there is the AGN flare program. I will now go through some AGN physics questions at very high energy gamma rays, and I will there on the way mention how these different observational strategies are relevant for addressing those open questions. But first, some basics. So as I already mentioned, the AGN, when the relativistic jet of the AGN is pointing very close to our line of sight, we call them blazars, and they are extremely bright gamma ray emitters, both in the high energy and very high energy gamma ray sky. They are luminous and distant, therefore they are used as beacons when we study, for example, the extragalactic background light or intergalactic magnetic field or fundamental physics questions. But there is relevant open questions on AGNs themselves, and these are, for example, the composition of jets, mechanism of flares, location and physical conditions of the emission region and emission regions, and I'll slide through these questions in the next slides. I start with the composition, and actually this is a very long-standing open question. So it has it is still unclear if the relativistic jets in the active galactic nuclei are made of electron-positron pairs only, or there is also protons. And this, of course, the existence of protons or not is very closely connected to the question of emission of neutrinos. So in theory, AGNs are excellent candidates, as the jets are known to accelerate, to emit neutrinos and to host and to therefore be also sources of ultra high energy cosmic rays, because they are known to accelerate particles to high energies. But again, we are not sure if there are protons there. On the other hand, we do see ultra high energy cosmic rays, and we do see ultra high energy neutrinos as seen by IceCube, and the origin of those particles is still unknown. As we all know, the two link very closely together because the neutrinos are produced when relativistic protons interact either with photons or with target protons. Very high energy gamma ray observations together with neutrino observations are really the only way to scope also the origin of the ultra high energy cosmic rays, because unlike the ultra high energy cosmic rays, which get absorbed and or suffer losses and get deflected into magnetic fields, the very high energy gamma rays and neutrinos actually we can observe from the ground, from the direction where they were emitted from. And I guess everybody is very familiar with this one case, very famous case, where the Ice Cube Neutrino Observatory detected a neutrino, this neutrino was emitted quasi-simultaneously or was observed quasi-simultaneously with a flare in the very high energy gamma rays and gamma ray band as observed by imaging air Cherenkov telescopes and Fermi satellite. And this temporal coincidence and the directional coincidence then gives us the 3 sigma certainty that these events were related to each other. And this is pretty much the only case. So this is the name of the source, DXS0506, is the only case where we think we have a detection of a neutrino blazar, but it's just one source. So there is certainly many open questions related to this question that can be then further follow up with CTA. Then I move on to the population of very high energy gamma ray HENs, and I start off as we know it today. So we know almost 100 very high energy gamma ray emitting HENs. Here you see kind of a family portrait of the population. So the sources where the synchrotron, so the spectral energy distribution of blazars is always characterized with this 2-bump structure. And the sources where this first peak, which is due to the synchrotron emission, where this peak is located in high energies, are of course the most favorable for us to be observed in the very high energy gamma rays. And this is what we see then in the current population of very high energy gamma ray HENs. So of the population of approximately 80 sources, more than 50 belong to this HSP class. On the other hand, as you can see, there is plenty of other subclasses, and for all others of them, we know only handful. So the extreme HPLs that are very important for our understanding of the so-called blazar sequencing phenomenon. And then on the other hand, the most luminous ones, so the low synchrotron peaked objects and flat spectrum radio quasars, which are highly Compton dominated and therefore very interesting for many purposes, we know only very few. There are also classes of active galactic nuclei, that we have not seen yet with the current generation of telescopes, and where there is but might be of potential interest to us and should be discoverable with CTA. Those include, for example, narrow-line Seyfert-1s, a type of active galaxies that seems to be hosted by spiral galaxies, with much smaller black hole masses than what we see in the normal blazars, which are hosted in elliptical galaxies. So the narrow-line Seyfert-1s are very special case, but they seem to host a relativistic jet, which is very variable and could be therefore of interest to observable also by CTA. Other class is the low luminosity HENs, which we have not detected in the very high energy gamma rays yet, but could be within the scope of within the reach of CTA. And here I will, in the next slides, I will show few plots, few tables about the numbers of what that might be of within the reach. Our estimation based on the extrapolation of the Fermi spectra on the numbers of HENs that we can observe. So first, let's have a look at the total numbers. As I say, the total number currently is around 80. with CTA, even if we would point only 5 hours to potential sources, we would already, within our reach, there would be like 400 HENs, and of course the number becomes larger when we use longer exposure times. It's not just the increase in number, it's also in the increase on how we understand the HEN population in the very high energy gamma rays. So of course, as I explained with the current generation, we see mostly these HSPs. This will of course be true also with CTA, but you can see that of the blazars of the other classes start to be there as well. And this is the numbers I'm showing here from the ICRC presentation in 2017. We are currently revisiting this number, so stay tuned. It's using new Fermi data and also using new analysis tools. I will show also a plot on how the HEN population will look with respect to redshift, and you can see that while the current population we know ends at redshift 1, with CTA we should be able to go to higher redshifts, significantly higher redshifts. I would also like to point out that there is a very large population in the Fermi catalogs of blazars for which we don't have redshifts, and CTA consortium has started a major effort to get major observational effort to get redshifts for those, and we have just posted on arXiv our first results. So if you are interested in that, please have a look. Then I move on to the question of the location and emission models, which are different for different HEN types or different subclasses. So if we look at the cartoon of the central region of the HEN, there is the central black hole, the accretion disk, and then the accretion disk is powering different regions around the central engine. So for example, so-called Broadline region, and then dusty torus. And these features are, so especially the accretion disk, but also the Broadline region, they are very efficient. They are good sources of seed photons for inverse Compton scattering, but they also are very efficient absorbers of very high energy gamma rays. So any emission that is emitted too close to those cannot be observed by us. So the normal paradigm is that when we see very high energy gamma ray emission, it must come outside from the Broadline region. However, we also see from the spectral energy distribution of flat spectrum radio quasars and low synchrotron peaked sources that to explain the observed spectral energy distribution, we do need external photons. The simple synchrotron self-Compton is not enough to explain the spectral energy distribution. And as the availability of this external seed photons, so for example from the dusty torus, does depend on the location of the emission region within the jet, then it's of course of highly relevant. The emission model and the location go hand in hand. For high synchrotron peaked sources, so the most numerous ones, we don't have such a problem with the seed photon fields because we know that the Broadline region, if existent even in these sources, is very low luminosity and is not even efficient enough to absorb anything. But there, and also we do not need the external seed photons to produce the observed spectral energy distribution. However, there is a different kind of complication in their emission models, and it seems that to explain the spectral energy distribution, it's extremely relevant to have more than just one emission region. And this is, by the way, also true for the low synchrotron peaked sources and flat spectrum radio quasars, that there seems to be observational indications that there are more than one emission region. And both of these questions also affect the intrinsic very high energy gamma ray spectrum that is emitted by the source and is therefore of high relevance to when they are used as beacons. And therefore these questions are of high scientific interest, and to address this we are planning to perform this long-term monitoring observations with CTA. And in order to answer the questions that I mentioned here, we also need this CTA monitoring observations to be supported by multi-wavelength observations. Then I move on to the next open question in HEN physics, which is the fast very high energy gamma ray flares. We see them from flat spectrum radio quasars, BLX, and radio galaxies, so from all types of the sources that we know today. When I say fast, I mean variability timescales less than 30 minutes. Fastest we see are faster than 5 minutes. So here is, for example, one example from radio galaxy IC310. Here is one from Parks 2155. Here is one from flat spectrum radio quasar Parks 1510. We do not know what is the mechanism. There is many suggested. So, for example, the emission region might be extremely turbulent, or there might be a magnetic reconnection going on. And the superior sensitivity of CTA will be the key to discriminate between these different models. And in order to discriminate these different models, we need observations of many of such flares with the superior sensitivity of CTA, because due to the stochastic nature of this phenomenon, we need to address this question statistically, and that's why we need many flares. We cannot resolve just by observing one extremely bright flare. This is one of the scopes of the HEN flare program that I mentioned as one observational strategy, and we are currently working on simulations on how CTA will be able to resolve the acceleration and emission mechanism in blazars. So I ask you to stay tuned. We have also a strong involvement from the Indian group in that task force. Now I move on to the Tamarai Cosmology very shortly. So as I said, the HENs can be used as beacons and also Tessima-san was discussing this point. So the HENs can be used as beacons in the gamma ray horizon to study the universe between us and the blazar. And this happens when the intrinsic spectrum, and I was describing you that there are some issues that we don't currently understand about the intrinsic spectrum and should be solved. So when the intrinsic spectrum is emitted by the HEN, then the very high energy gamma rays, as they travel through the universe that is not empty, some of them will get absorbed by the extragalactic background light photons, and the spectra that we then measure on Earth is not the one that was originally emitted, but will have some features. The absorption depends on the redshift of the source and also on the energy. So the horizon, so how far we can see in the very high energy gamma rays depends on energy. So the further we go, so if we are observing, for example, redshift 1 sources, then we can see them only at below 200 GeVs or so. We have a very recent CTA consortium publication on what do we expect from the EPL constraints using CTA, and this was and I would like to point you to this reference here. And in that paper, we studied the EPL resolution with CTA by simulating Fermi-LUT sources with where the opacity is larger than 1. And then it was used the spectral extrapolation with intrinsic cutoff depending on the redshift and source type. And in the simulations, we used both the steady sources and GV flaring sources plus flaring sources in HEN, so in the TV band. And so this is the current, as I mentioned, all blazars we know are variable. And we used a certain EPL model to test the limits. And the simulation, the total observing time that was of CTA that was used in the simulation is 830 hours. And here it is how it is divided to different observational strategies. So this is an enormous program. It cannot be performed in one year only. So this is a long observational program with CTA to obtain extraordinary constraints on EPL, which I'm now showing here. So this is the results as of what do we expect from CTA. As was already highlighted, we expect the constraints on the EPL to extend to much higher redshifts than with current generation. And we expect this, of course, these limits to be much tighter than what we have from the current observations. In this paper, we also discuss science questions of as of how CTA HEN observations can be used to scope the intergalactic magnetic field, which I did not mention. So of course, the charged particles that are formed in the pair production, or closer to the HEN itself, they are deflected by the intergalactic magnetic field, and this effect can be used to study the intergalactic magnetic field. In addition, the HENs can be used to search for action-like particles, another topic that this consortium publication is discussing, but I actually don't have time to discuss that. So I point you to that paper for the details on those limits that what do we expect from CTA in that sense. Now I move on to extragalactic survey. And here the take-home message with what I will start is that this will be the first unbiased view of the extragalactic very high energy sky with unique sensitivity between 100 GeV and 10 TeVs. This is something that has not been done with the current generation and cannot be done with the current generation of telescopes either. The plan is to perform a blind survey of 25% of the extragalactic sky, perform it with superior sensitivity. The uniform exposure should allow us to go to the sensitivity of about 6 milligraphs. And the plan is to observe each field of view with several pointings to spread over 2 years so that we can average over source activity states. So as I mentioned, the sources that we know in the extragalactic skies nowadays are all variable. Almost all are variable, sorry, not the starburst galaxies. And the main goal of the extragalactic survey is for example, the measurement of the luminosity function for nearby very high energy gamma ray blazars, estimate the diffuse gamma ray background, but of course, this extragalactic survey is also to search for the unknown. So we expect the unexpected results to come from this survey. It will be also a very essential tool for the very high energy gamma ray discoveries. Finally, I have a few slides about the transients. So here, Teshima-san was already talking about gamma ray bursts, but as those are the up to now only very high energy gamma ray extragalactic transients that we know, that's where I will also focus on. But I would like to point you to that we are also currently performing studies of what do we expect from CTA on the gravitational wave follow-up, for example, on neutrinos, on galactic transients that Luigi already mentioned, and other sources, so also optical radio transients, high energy neutrino transients. And of course, we also expect to detect serendipitous very high energy gamma ray transients with CTA. So the whole point of the transient key science program is that with CTA, we should have the far superior photon statistics compared to Fermi-LAT, just above just few GeVs. And when we do that, and that will of course allow us to reveal completely new physics from the transient phenomenology. And I will take the gamma ray bursts here as an example. So we all know what the gamma ray bursts are. They are death rolls of massive stars, and they are observed at sub-MeV range. Up to date, much more than 1,000 are known. So one might question that, gamma ray bursts at gamma rays, what is the thing there? I mean, of course,
Elena, how much more time you need?
I think this is my final.
Okay.
Yeah.
Yeah. Okay. Fine.
Yeah. Sorry. So currently, but it is an issue to observe very high energy gamma rays from gamma ray bursts. And actually, we had to wait almost 15 years before we did, even in the current generation of telescopes, we did get any. Currently, we know 4, and they are listed here. So what did they really reveal us? So this is the GRP 1901 14C, which also Decimus-san mentioned. This is from the MAGIC collaboration publication in 2019 from Nature. So when we, with the MAGIC telescopes, was able to move to the target very quickly. And here is what we see. Plenty of very high energy gamma ray photons, of course, largest numbers in the as we first arrived there, but still some after 100 seconds. And sorry, 1,000 seconds. And these observations did reveal completely new emission component of the GRPs. So this inverse Compton pump here. And we also expect in the future these GRPs to be very valuable for the EBL studies. So this one was rather close by, was around a redshift of 0.5, unless I think. But of course, we should be able to detect GRPs all the way up to a redshift of 2 with CTA. So that will be highly available for the EBL studies, as they are distant and bright. With CTA, like Masahiro was describing, we will have fast automatic reaction, slewing speed of less than 20 seconds to any point of the sky. And this should give us a rate of few GRPs per year. And I'm sorry I did overdo my time, so I will just leave you my summary and invite your questions.
Yeah, thank you very much. We can allow for quick and short questions. Any pressing questions? Amit, do you see?
Yeah, there are questions. Yes, Prajwal, please go on.
Yeah, so my question was to do with the new physics that can come out of the very high energy flares that CTA can observe with much higher sensitivity than before. So your pie chart suggested that you will spend some amount of time monitoring already known flaring objects, but is there a strategy to actually catch the source when it is flaring on time scales, of the order of 100 seconds or so, because that seems to be the most exciting and unknown part of this.
Thank you for the very good question. Indeed, I didn't have time to touch upon that. So the whole HEN flare program is planned to do that. So, and then of course, the obvious question is, where do we get the alerts to point to the sources when they are flaring to catch these fast flares? And in the current generation, this is very much done based on triggers, for example, from Fermi. but we know that there is no one-to-one correspondence between Fermi and the very high energy gamma rays. So of course, the best thing to do is to get the triggers from the very high energy gamma ray band itself. And one possibility, which also Tessima-san did mention, is that magic telescopes would stay and monitor and alert. That would be a great opportunity for us. But then other possibilities that we did envision in the key science program is that we would be doing some kind of snapshotting using CTA itself as sub-arrays to look for the flares. But that, of course, it would consume a lot of CTA observing time. So if there would be a dedicated monitoring instrument to look for flares, that would be actually the optimal. And now that you did ask this question, maybe I also may answer your previous one with my own, so the one you asked from the Teshima-san. So you were asking about the sources that might be observed both by north and south. And here I think that for extragalactic science, the most interesting flares that we might see, we would see them first in the north because of how the Earth rotates. So and it would be, of course, highly valuable if the visibility would be good also from the south, so that when it becomes non-visible in the north, the southern array could continue and we would get continuous observation of a source, for example, for 12 hours or something like that. That is something we have in very rare cases with current generation and would be highly valuable for many physics.
Yeah, thank you.
Any other question?
Seems to have that we do not have any other raised hands,
Yeah.
So we can conclude this session.
Yeah, okay. Thank you, Elena, for your talk.
Thank you.
Yeah, I thank all the three speakers who were giving a very good talk on on CTA and informing us about the current situations. Okay. I'm sorry that we overshoot by 15 minutes. I'm sorry that we overshoot by 15 minutes.
That's fine, sir.
Okay, you carry forward.
Yeah,
I declare this session closed.
Thank you, sir. I thank you and all the speakers for the session. We'll take a short break and maybe have a tea, and we reconvene after 10 minutes in Indian Standard Time at 16:15. So we'll take a 10 minutes break. Thank you.
Last session of the workshop, and we have two talks in this session, one on CTA computing and the other on the activities ongoing in how to analyze the data once data would be taken by CTA. So the first talk on CTA computing would be given by Stefan Schlangstadt. And so please, Stefan, I hand.
Yeah, thank you, Pratik. So my talk is, of course, very different from the previous talks, much more technical and very detailed. So you will see, but we have a big task ahead. So this is, of course, a slide that you know. CTA, Interoperability Telescope Array, it's an observatory that is call it 20 to 50 times bigger than the current installations. This is Hens Magic Veritas between 2 and 5 telescopes. And the only way to increase the goal to have these higher sensitivity call it 5 to 20 times, depending on the energy, is to build more telescopes. And this creates, of course, a lot of, let's say, technical problems, also with the goal of operating the observatory for 30 years. The observatory aspect is also new because it's not a consortium or experiment-driven approach, but it's an open observatory in a sense of proposal-driven observatory, like whatever Fermi and the ESO telescopes, always, of course, a little bit different. I don't want to talk about that much about the technologies. It was shown by Masahiro Teshima, but the key is we have many telescopes of different sizes, and that's an let's say a logistics and integration problem. But if you concentrate on the lower part of the slide here, you see data rates in kilohertz range between the different telescopes, but you see also the readout of and the sampling rates that basically drive our data rates. The observatory itself as a legal entity is described by Masahiro earlier. It will instrument, this entity will operate the instrument over 30 years. The data will be stored much longer than that. It is an observation. It's a proposal-driven observatory with guest observers, consortium, observatory users in different schemes. This is all negotiated in the creation of this new legal entity. The observatory is responsible for the science user support, so science tools, how to create images, spectral light curves, also provide high-level science data. And I will talk quite a lot about this later in this talk. The data will be public after a predefined proprietary period. So the PI asks for an observation, and typically after a year, the data become public and are in the archive in open data format. And of course, this will be compatible with virtual observatory standards. I will talk about this later. The major challenge, as I mentioned, it's not only it's an open observatory with a long lifetime, but it's also it has a very distributed environment with 2 sites, and one on La Palma, one in Chile. Science Data Management Center and the headquarters in Bologna. I will show you. It was here on the previous slide. The upper picture was the headquarters in Bologna. The lower one is the Science Data Management Center will be built in the next 2 years in Zeuthen, close to Berlin. CTA requires naturally a well-designed software system to operate that many telescopes, 60 or more than 60 over 2 sites in the next 5 years. Later, hopefully much more, as a single efficient system, right? And of course, it is clear that people who write the software today won't be there to maintain them in the next in 5 or 10 years. So that has to be really well tested, documented, etc., etc. So that's a software challenge. It has also a data aspect, a data challenge. So we start with a few petabyte of year of raw data, much more in simulated data, and many petabyte, as I said, 20 petabyte of simulated data, but the real data that the user will get is much smaller. So the high quality science data products have to be tested and delivered together with the tools to understand and analyze these data. This is a very complicated and transparent planning system needed between the CTO, in particular the computing department, with the people who write the software. This is organized typically in CTA with in-kind contributors, so institutes to deliver pieces of software in some way contractually bound. And of course, we have industrial partners as well. So we are now in a process of writing software prototypes, and this has to be rolled out as quality software. And the key milestone for us is that the first telescope that Masahiro Teshima talked about, the LST, it's already installed, it's taking data in a prototype mode, but the telescope acceptance will either happen later this year, most likely early next year, and this will be followed by early science. The department is organized like you see it on this screen in light blue. You see on the right the connection to the cybersecurity officer or information security officer. I will talk about this later in the talk. So apart from the coordinator, we have an architecture group. I will talk pretty much quite a lot about architecture in this talk. We will see a lot of graphs and I will explain how we do it. Then, of course, we have an infrastructure team for identity management, release management, etc. And in the bottom, you see the different working groups or work packages in computing and on-site, off-site computing and array clock. I will talk about a few aspects there: array control, data processing, then science user support, and technical operation support. So I will cover most of the blue boxes on the lower bottom here in this talk. So if you think how the real world looks like, or at least the world we dream on is look like, you see in the upper view graph, the desert where we have our telescopes, be it 4 LSTs that Mother Hero talked about quite a lot, 25 MSTs and medium size, and then a lot of small size telescopes stretch out over a large area. They produce with a rate of 600 gigabit per second, locally 1,000 petabyte a year. This goes to on-site clusters. So we have an on-site cluster with, let's say, an order of 1,000 cores, or a little bit more, where we process the data, reduce the data. I will explain this a little bit, and then ship data out over a limited bandwidth to the off-site world, where we store the data, raw data, on the level of a few petabyte a year, make them ready for reprocessing, calibration, data quality. Again, it will be reduced to a level of a terabyte a year for the science users. And this is, of course, what the observatory is. The observatory basically delivers data to not only the PIs, but to everybody, like many other observatories, of course. So just a few words on simulation. So we produced whatever 20 petabyte, order of 20 petabyte of simulated data, both during the construction phase. I will show you a few graphs in a minute to characterize the site and study the performance, so that the science groups that you talks about have something to plan. And then, of course, in the operation phase, we need these Monte Carlo simulated data to produce the instrument response functions. We plan for run by run simulations, and of course we need it also for validation of new algorithms and software versions. So the production of Monte Carlo is done in a mixed structure of grid and non-grid resources using the Dirac Interware. Dirac is a software that was written originally for LHCb, but we use it heavily. It's many groups are using it now, also in linear colliders and Bell, etc. So we have CTA extensions for that. It's supervised by the project scientists of CTA, but also in the consortium with the analysis simulation working group. It will be under control of the simulation sub-package of CTA. It is currently done with service level agreements with computer centers, the usual way it works. So we basically get pledges once a year how much resources are needed, and then we store the data and analyze them for CTA. This will be an in-kind contribution. I will talk briefly about this later. And this Dirac, this Interware, is a software that will in the end be used in CTA on many different layers, particular for the production of data as a workload management system for and for the simulation in many different occasions. So the use of the Monte Carlo here, you see site layout studies that was shown earlier in the earlier talks. So there's an example configuration on the left upper view graph for the north. There's one for the south. And then you see here angular resolution and energy resolution and the effective area. Then you calculate the instrument response functions and then create a sensitivity. And what was done in the past, for instance, we used this to create this beautiful science book, Science with CTA. It's a major effort, and all the studies that were shown today were based already on first studies published in this book. So the data flow is shown here. So we start with telescopes, as I showed you in this pseudo picture before, but then we go to data acquisition. We take the data, we make a real-time analysis, we store them locally. That's done in a work page called array control and data acquisition. I will show this later to you. And then the data are processed and stored. And this is done in another work package called data processing preservation. And the science data are done dealt with in the science user support system. But of course, we have an outside world, other observatories, and our observatory users. And you see here a lot of links on alerts that we generate ourselves, alerts that we send to other observatories. In one of the questions, this TO question came up, and that's of course the context of that here with this blue arrows, alerts from other observatories. The view from the user is, if you concentrate on this PI picture, people make a proposal, the proposal is handled, then the data, there's an observatory planning. We make there's a long-term plan, there's a short-term plan, and we take the data, process them, and then we store them. This combined with simulations for understanding of the instruments, and make a final processing, and we have in the requirements yearly reprocessing, and then we store the data and hand them over back to the user or to the PI who asked for the picture. And of course, this is done. The handover is done in archives. I will talk a lot about archives in this talk, and then different data levels that will be explained later. And of course, all this information is to kept somewhere, and that's what we call the science operation support in the center of this wheel. So that's the whole picture of CTA. This is the system view of CTA. You see telescopes here, but there's only one aspect. The red block boxes are what computing is, but of course there's much more. There's calibration devices. There's of course a management aspect. There's a protection system, integrated protection system, safety place, but then that's only part of it. Some of it is at the sites. This is in the bluer bubble, and then some of it is off-site with the headquarters and the science center management and the data centers. The view again from the data flow is shown here. We have the two sites. We store the data. We send them over with always higher condensation. This is the data formats I explain later. Then you do final processing here. You store the data, and so it's the same view again as a linear presentation. And you see here this has happened on the sites, and this has happened externally. With a strong data reduction, it's obvious that we cannot store these many petabytes, and so we have to ship. We can only ship down a few petabytes a year, and then in the end, it will be gigabytes that will be handed over to the users. And then the data will be there will be an access to the user through a science portal, so that the data have an easy access to the data, but also including the software that can look at these data. There are a few different categories. This is a real-time aspect that's in minutes. There's a next day data product that is already of good quality. That's basically a level of day, but the final production of the data, full calibration, best calibration, reprocessing, it's a few weeks to a month. And so this is basically how we structure the data. A corresponds to on-site, B is the first level on-site, and C is then finally off-site. And here you see, I don't explain this in detail, the data levels that go from within the camera to handing over to computing, and then this is our treasure, the raw data Dl0 that we store and reprocess, and then it will be getting refined and refined. I will show you this in a second. So just to tell you that there's a site, and you see on the right side what work package is responsible for that. The formal description of this is done in data models. This is very important that you store the data not only efficiently, but also in a very clear description, including metadata and relationships between the data. And then, of course, you have to take into account already, let's say, early alerts, et cetera. And you see here a picture of this data model that is a published document. That is in the upper column. You see the event data that is from left to right is going down. It's concentrated more and more. Here is in monitoring data and the service data. Here is, for instance, the Monte Carlo instrument response functions I meant. And then for high level, it's getting more and more concentrated, and you end up as catalogs and sky models and data cubes on the very highest level. And of course, this has to come together with metadata. It's on the left. So who is doing what, the provenance, what process did what to what process. So the first package I want to describe is the array control and data acquisition. That's the supervisory control system that deals with the instruments. It steals the documents, it reads the data out and compresses the data and generates automatic science alerts. So you see here a full view of that. You see that on the lower side, you see that the telescopes push data into what we call the array data handler, a data acquisition system. That is, of course, monitored. Then we make a quick analysis to generate both the science alerts, but also make a quick data analysis. This is all coupled to the short-term scheduler, through a central control, to an operator interface. So you see it's a pretty complicated system, and it has, of course, a context. That's the main data flow in a Cherenkov camera, but it's maybe a little bit too detailed for this. But the context here is that the array control system in the center of it has to deal with handover of data to other workbench that I talk about in this talk here, but also to operators and to other facilities, to laser traffic control systems, if they're, for instance, if there are big laser calibration lasers nearby, like be it from the TNT or ELT, we have to avoid that. And this can be, of course, seen in a more details here in a full context view where you see also all the interfaces that we need to describe that. You know, I don't want to go through this, but I'm just saying this is our architectural view of that. And I will explain this here. The architecture we built is based on this SBS methodology. So we start with the requirements use cases on the left here. You see that here. Create a context view that I showed you a minute ago. Then we make a functional decomposition and the local decomposition. And so this is our way to basically represent and plan our software. And of course, from there, you come to all the interface, documentation, etc., including vision sharing, scoping, describe the scopes, and describe the important ingredients for collaborative software engineering. One of the main aspects here, hang on a second. Sorry for that. I'm sorry for that. One of the main aspects is that we have to tag all the data that we take with a super precise timestamp, not only for triggering, understanding the telescopes that are 100 meters apart, but also to talk to the outside world. We have for that a master clock system that provides absolute time information for the comparison with external facilities. Then, of course, we have a logic, let's say a standard NTP protocol to take events in the calibration systems, and we have a nanosecond precision clock system. And you see here a picture of that. The clock system starts, of course, with a GPS. The technology we choose is White Rabbit that comes from an accelerator department, started at CERN, but it's used also elsewhere. The time is both sent over the network to the cameras, and then it's basically also sent to the data stream. And so that's it's a small component, but it's super important, because without this really precise clock, we cannot understand our data. So the data are then shipped to the offsite world. This is this work package called Distributed Data Processing and Storage. DPPS that manages the data is responsible for processing to a smaller size. I gave you a few numbers earlier. Also responsible for simulating the data and for reprocessing. And it's a complex chain of algorithms and runs in parallel. Here you see an architectural view of that. You see the pipelines here on the left in yellow. I will talk about this again in a second, but of course you need to store the data. That's this archive system. This also includes the file transfer. You see here the ingest of the data from Arcada, the previous work system, then you ship them out to the science users, but of course it's heavily connected to the infrastructure. I will show you later how this is done. I talked about the Rakta workload management system, and then of course this defines the workflows and the interfaces in the same way. The concept is really that we start with the site centers, then we go to offsite data centers that I will talk about later, be it grid or non-grid. It's not important, but then of course it has to be, the data has to be processed with a management team, all the 4 pipelines and that I talked about earlier. It's a distributed system. It works as a cloud. It's centrally managed in a science data management center. The software is running at multiple sites, and we call them DBPS nodes that they run locally and on-site and off-site. The software is broken into basically 2 big blocks. It's a middleware, so it's common libraries, computing resources, etc. And the pipelines that I mentioned, there's a simulation pipeline to produce simulated data processing. That is really the core of the processing, to calibration. It's a super important pipeline, and of course data quality that we know that we take high quality data. The pipelines have a very similar structure: frameworks, tools, workflows, database, and then of course we have user interfaces on top of that. The concept of the pipelines is shown here. So the simulation, the core is the data processing that takes data from the real world on the top, or from some simulation in the same way, is reducing the data and giving it out to the user support. And I will talk about this in a second. Calibration and data quality on the bottom. And of course, this takes data from the calibration instruments, but also from the cameras. These are data taken. That's a complicated process of LiDARs and weather stations, but also the camera itself, flat fielding. You do all kind of calibration with the data taken, or on a, let's say, a monthly basis. That's a different issue. So the core of all these things are the archives. So we have 2 archives. I talk about them in a second. But of course, they're connected with metadata to know, how the data are produced. This is the provenance, and we store also the proposals and the schedules in there and the status information. And we need to archive also the monitoring engineering data. So there's a lot of work done in the past, both in CTA in previous years, but also in prototyping work and framework of European process. And the data usage is very different. We have basically what we split it up in the bulk data archive and the science archive. One is the outcome of this data processing work package that I talked about a minute ago, and one is the science archive that I will talk next. These are of course smaller processed data that you saw already in the data models there. And it is very clear that the science user or the end user need a very fast, flexible, query-based access to the data. And you see this is here in the, let's say, call it different use cases. So in the bulk data, I have a large amount of data, tens of petabytes, small number of users, ODD experts, the guys who do the processing. And there is no need to be maintained after the end of CTA. A few years, but then we have the long-term preservation. That's of course our science output. This will be maintained more than 10 years after the data are used. There's a large number of users. We talk about a few thousand, and they will outlive the operational life of CTA. So the standards we use there are these. You see here, this is the Open Archival Information System on the left, and here the Virtual Observatory standards. And everything we do has to be following the FAIR principles. That's findable, accessible, interoperable, reusable. That's something that big observatories talk now all the time. And this OAS is not only, let's say, a standard, it's also a model implementation with definitions, best practices. And this will, the key is that we talk about information, not about files. So we distinguish between 3 information packages. This is submission, archive, and dissemination. And you see here the relationship in these arrows. The basic unit, as I said, is the information package, content, preservation, provenance, basically to know what was done to the data, the context, the reference, etc. So that's the underlying concept of our archives. These things are done in an offsite computing world, where and I show you here a few examples of we do the processing workflow with a few assumptions, like the load sharing between data centers, and how to verify the compatibility. So we take the data from the site, process them, duplicate, replicate them, and then we have to remove the data on site to take further data. And before we do that, we have of course shipped the data from the sites to Europe. The Chile site is here. You see on the right view graph, this is where this blob is. The most likely path is going down to Santiago, going over to Brazil, going to Argentina, going up to Brazil, and then ship it out to Lisboa, and from there to Spain, and then you're in the European networks. The alternative path, or the path of the past, is here. You see here with the US, it will be a redundant path, and this here is basically relies on an underwater cable called produced in the Bella S project. La Palma, of course, is a bit simpler. There is a fiber connection between the Canary Islands to the mainland, and that's an established path already. The data center itself, we're refining the model now. At this point, we talk about most likely 2 and not 3 data centers, but it's all driven by considerations that you see here on this graph. So the data come in as raw data to the data center 1, then you put them to tape for safekeeping. You copy them over to a second data center where it's put on tape again. Then you start to processing the data to a higher level, put the data on disk, put the data on tape. Then you store in the second night, you go to another data center and you do the same game there. And so you do this ping pong mode. And you have to have, of course, 2 full copies before you delete the data on site. The science user perspective is, of course, different. They should not know about any of this. So there we have the archive users and the guest observers. So how to prepare. So you see on the upper part how to prepare and submit proposals to take data. These data are prepared and for data submission in a long-term plan and a medium-term scheduler. And then, of course, the data has to be documented. There has to be a help desk. And that's, of course, a very different aspect, but that's basically the user side that the observatory provides, and the users get in the end photon event lists or candidate event lists in FITS format. That's our current thinking, including the instrument response functions, the background model, and then, of course, very important, the science analysis tools and supporting documentation, what to do with these data. So this is done in a work package called Science User Support System, and that's responsible, as I mentioned, for proposal handling, long-term scheduling, for the processing of the high-level data, for the archive that I mentioned earlier, the science portal, how to get these data. And of course, this was discussed earlier in the previous talks and in discussion, support multi-messenger observations, support target opportunity, and heavy communication and MOUs with other observatories. That's the architecture of this science user support system. Basically, you see the same sub-work pages as described before, but you see also a lot of interfaces and dependencies between them. This science user access is, of course, the major interface, as I mentioned, between the observatory and the scientific user community, including the guest observers and the archive, the users to perform a successful, allow the users to perform a successful scientific analysis, needs some user support, including dissemination of high quality software that we call the science tools and the proposal handling. That's the repetition of the same thing, but one has to keep in mind this, that we have the designated community, or the community of the observatory. These are consumers or physicists who are able to understand the information via the knowledge base in these two archives that I mentioned before, in particular here, the science archive for the community. But of course, this designated community might change over time, depending on the use cases, depending on the budget. And so the question is, in the end, what are the proposals in what the different countries that are organized in CTO can afford for the next years. One important aspect that I cut short here is the interoperability. So that's of course in a time where SKA has built LSST, starting, Vera Rubin is starting to take data. So of course it's not only that we exchange information and we exchange data in the end, but also we use the same standards and develop prototypes together, be it in the virtual observatory as world, or be it in following the European programs that we are part of. So the way the software is organized in CTA is that the observatory is responsible for the construction, management, architecture, design, specifications, definition, quality assurance, and testing. That's all CTA, this observatory responsibility, but the software itself is delivered in our current model with in-kind contributors, so members of institutes, group of institutes. In Akara, it is 8 institutes or 10. In DPPS, it will be more. In ZUS, it's also 10 or 15. So all in all, it's an enterprise of more than 100 people delivering software. So it needs quite a lot of coordination, including quality assurance, testing, integration, and this is done in a model where CTA delivers, let's say, guidance and coordination, and the software is written by the institutes. An aspect that I won't discuss in long detail is the cybersecurity. You hear all the time about cyber attacks left and right. So we made a workshop already 1.5 years ago on cybersecurity. It was starting to concentrate on control systems. Remember, for instance, IceCube was hacked many years ago, et cetera, et cetera. Every night, CERN and all the other institutes in the world have massive attacks from hackers. So we should be really safe and that they don't destroy either the instruments or the data. And so we will hire a cybersecurity officer or chief information security officer that will implement policies, and that's on our list. So just to summarize, so there are major challenges ahead to get ready both on the sites in the Science Data Management Center and the headquarters to create an open observatory with the user service and support in the core. Of course, it needs to be really well-designed and tested software, well-documented software to manage more than 100 telescopes in a single efficient system. We do this technically with data challenges where we already test before we even go out all the aspects of software and data handling of these several petabytes of year of raw data. And then with a transparent planning that is well communicated to deliver quality software to do the first early science in the next year. Thank you.
Thank you, Stefan, for a very nice and a very detailed talk on the computing.
You give me 35 minutes, I fill it, huh?
Thanks. No, thanks for keeping the time also. So let me see if there are questions. At this moment, I do not see any raised hands. Okay, so maybe I would like to ask one question quickly. Have you given any thought on getting cloud computing from the cloud service providers in order to do all this? You know that IceCube very recently has been able, or a couple of years ago, has been very able to use a lot of computing from the cloud providers. Is there any thought going on in this direction in CTA?
Yes, yes. The problem is that, yes, sure, but it's a cost analysis, right? You know, if we exploit the big data centers that are in a collaboration, be it DAISY, Barcelona, Lyon, whatever, you know, we have one in Italy. So then our hope is with established techniques, we are able to deal with it, but it's for sure everywhere, as you say, not only in IceCube, also at CERN and Fermilab, where people use to exploit cloud computing, and we're making a cost analysis. Currently, for the first years, we will go for data centers offered in the in-kind contribution context by the different member states, right? But in the long run, we might follow the movement everywhere to go to cloud computing. You know, it's clear that Facebook and whatever Amazon have computing resources we can only dream of, right?
Absolutely. Yeah, I agree. Yeah, I understand that. Yeah. Okay.
But currently, for the next years, that's not our main goal. But you know, it shouldn't be a problem to move to cloud computing later.
Okay, I see.
It's a cost benefit analysis.
Yeah. Yeah. So let me see.
Computing later.
Okay, I see.
It's a cost benefit analysis.
Yeah. Yeah. So let me see if there are any hands raised at the moment. I don't see any. So okay. So thanks again, Stefan. So we move on. So our next speaker is Atreyi Sinha, and she will be talking about the data analysis for when the data would start to flow. So Atreyi, please.
So thanks a lot, Pratigda. I will try to share my screen first and see if everything works fine. So do you see my screen?
Yes, yes.
Okay, good. So hello, everyone. Good evening, good afternoon, wherever you are. This was, the aim here is to explain how to do data analysis as the final PI. Once you get the data, or at this stage, how you do the simulations. Ideally, this would have worked very well as a hands-on session, but since that is too complicated to do online, we are doing it this way. If at any stage you have questions, please do ask, because even for me, it is otherwise a bit crazy. Otherwise, I will just keep speaking and not understand whether it makes sense to you. I am assuming that everyone is basically familiar with Python. If that is not the case, please do ask. And if there are any questions at any point, Pratigda, it would be great if you can tell me, because if I share the screen, I can't see the Zoom window anymore.
Yeah, okay, sure.
Yeah, so I repeat, please do not hesitate to ask if at any point something is not clear. So as Stefan just explained, CTA will have many data levels, which will go from raw images to what is finally given to the data. So first, the raw images will be calibrated, and the calibrated images will be called the level 1 data. This is where the CTA pipeline will work at this stage to do the data reconstruction, where you have reconstructed events after the HELAS parametrization, etc., which you must have heard today morning. Then there is the event filtering, where you take only gamma-like events. So when you go from DL2 to DL3, it is only the events which pass the gamma hadron cut. And from the DL2 event lists, the simulated event lists, you do the calculation of the IRFs. By IRFs, I mean instrument response functions. So you have the effective areas, the point spread function, etc. And this work is done by a package called PyIRF. And what is given to the user, what you will get is the DL3 data, which consists only of gamma-like events. There are no, so by gamma-like events, I mean events which pass the cut. So there will be gamma, of course, gamma rays and a lot of hadronic background, because many hadronic background disguise as gamma-like events, depending on whether you take loose cuts, hard cuts, etc. And it is this level which will be supplied to you. And then from DL3 data, what you would do is you would make reduced data sets like count spectrum or a counts map, and then do a modeling and fitting on it to make the science products like a spectrum, a light curve. And then finally, you can go to higher data levels where you make maybe a catalog or something, which is later. And the job of the CTA science tools, which can be either gamma pi or C tools, will start from DL3 and go up all the way. So my presentation here starts from DL3 and goes to the very end. So this DL3 format, consisting of gamma-like events and IRFs, this format is what we hope will be a common data format, not just for CTA, but for other gamma ray data as well. Hens, for example, already does a lot of extraction in DL3 format. Hawk is starting to follow this format. It is being adapted by Fermi, etc. Right now, it is a community-driven effort, and you can follow the details in this Gamma Astro Data Format page, GADF, and this will evolve as the CTA specifications are defined. CTA has not formally defined what are the specifications of it will need at the DL3 level. GADF is presently a guideline. It is based on the FITS data standard, which is very popular in X-ray astronomy and others, and it will follow the FITS convention for time. Everything is stored in specific binary tables. So what you would have is for one observation, you would have the effective area, the events, the energy dispersion, PSF, and it would be stored in different tabular formats. So for example, you will have a background HDU, and the background HDU would be saved at in terms of the camera coordinates and energy. You would have an effective area table, and the effective area table would be saved in terms of the energies and the offset and different, and so on and so forth. If you are interested, we can discuss this later after the talk. The CTA science tools assume that the IRFs will be given in DL3 format, and they are meant to perform forward folding. By this, it means that you take a specific source model, and then you convolve it with the detector response to get the predicted number of counts in detector. You see? So, and what you would really compare during the likelihood fitting is the predicted number of counts in the detector from what you get from the counts that you observe and the NPRED. It is very important to know that there are many experiments which follow backward folding, but that is not what the science tools in this case will do here. And the second hypothesis is that all the instrument response functions can be factored. That is, the effective area and the point spread function and the energy dispersions are independent of each other. In reality, they may not be, but this is the assumption that we use, and they are all functions of the true energy. So in high energy astrophysics, it is very important to make a distinction between the true energy, which is the actual energy at which you either do the simulation, or that is the energy which is the source is emitting this photon. And what you get in the detector is the reconstructed energy. And that is what we call ERICO. And how well this detector response behaves, how a photon of energy 1 TeV will be reconstructed on your detector. Maybe it will be reconstructed as 1.2 TeV, maybe it will be reconstructed as 800 GeV. What is this probability is given by the energy dispersion. PSF is something which most of us are familiar with. What is the spread of how does a point look like on a detector? And effective area is what is the area of the detector at a particular energy. So what you will get, as I was saying, is an events file which contains the events. And so what information is stored for each event is the reconstructed energy of the event, the arrival time, the arrival direction, etc., etc. You will get a GTI HDU, which tells you that so there are instrument responses associated with these events. And the GTI, which is the good time interval, will tell you whether at which times these IRFs are valid. Then there is a pointing HTU, which tells you where the telescope was pointing in sky coordinates, because the observations are, the source is transiting, the telescope is moving. Sometimes you have to correct for the observation, for the pointing direction. And the other IRFs will be the effective area, which is the effective response over the field of view, the energy dispersion, which is as a migration of E true by EVCO, and then the PSF and the background. Currently, we assume isotropic PSFs. Again, if CTA says that it will not be, we will have to move accordingly. And as Stefan also mentioned, there will be background IRFs, which will be supplied along with the at the Dl3 format, which says what is really the background, the hadronic background that is associated with this observation. With this, and constructing backgrounds are very difficult. We can discuss this again. And then you have HDU index tables, which tells you which IRF is associated for which event. You have an observation table, which gives you the details of observations. And it is the job of science tools to handle everything properly. So currently there are two proposed CTA science tools. One of them is called C tools, which is based on GammaLib and comprises a set of F tools like executables, which is developed mainly and at IRAP. There are, and with other people, of course, they have 1.7 version 1.7, which is already released. And I must say that I don't know much about C tools. I am a developer of GammaPy. For the remainder of this talk, we will concentrate only on data analysis with GammaPy. The latest version of GammaPy that we released a few months back is GammaPy 0.18.2. And to know anything about GammaPy, you can just see the GammaPy docs. And GammaPy is an open source Python package, which is built mainly using NumPy, SciPy, and AstroPy. And all the analysis is done through either Jupyter notebooks or Python scripts. So just to give you a brief introduction, what GammaPy does, as I said, it is based on AstroPy to do the coordinate handling. It is based on NumPy to do the data handling, and I mean data, the numeric calculations, and SciPy for interpolation, etc. It can take in data from different instruments. It is mainly meant for CTA, but it is not specific to CTA. It can take in data from Hens, from Fermi, from Hawk, from KM3net, from any telescope, given that it is in Dl3 data format. And more importantly, it can do a joint analysis. It can do a simultaneous likelihood fitting with the CTA and Hawk, for example. There is already a paper on it, we can discuss it later if you're interested. So this is the data from all these telescopes go into GammaPy, and what GammaPy gives you are likelihood profiles, phasograms, count, significance maps, etc. To do a setup, it's very easy. You can just again go to the GammaPy page. It's the installation is done using Anaconda. It's should be relatively easy. You define the environment, download the environment file. It should work immediately. With GammaPy, we are also shipping some tutorials where we got the permission to ship some public Hens data and some public CTA data, simulated data, of course, and some Fermi data, etc. And these data we supply with GammaPy so that you can do a quick analysis. And just to give you an example, so this is how you download the tutorials. Okay, fair enough. Now, how do you do the data analysis? As I was saying, so you start off with an event list where you have gamma-like events. From there, if you're doing a 2D analysis, you make a counts map. If you're doing a spectral analysis, you make a bin histogram in 1D or a bin histogram in 2D as per the case. And from there, you do a data fitting and you get flux spectra light curves. These two steps we have tried to keep as disjoint as possible, that either you have one data reduction stage and a data fitting stage. Traditional IACT tools, imaging telescope like we have within Hens, they really go from step here to here, and it's actually even further, and it's very difficult to do a cross check and see if two results don't match, at which point it fails. In GammaPy, we've tried to make it as modular as possible so that if there is a mismatch, you can really compare at any step. Now, what you must keep in mind is that while this looks very simple, even after doing all the Helios reconstruction or everything, CTA data will be background dominated. And background rejection is, of course, fundamental, by which most of the hadronic background will be rejected even before coming to the Dl3 stage. This will be only gamma-like events, as I'm saying, but there is still a strong irreducible background. This statistical background has to be subtracted at less than 1% level, and there are various techniques to do that. So we will go one by one to each of them. And how do you do the analysis? This is the analysis flow for CTA. And how do we implement this analysis flow in GammaPy? So GammaPy tries to follow this. Yeah.
Great. The question. Would you like to take it?
Yeah.
Prajwal, please.
Yeah, Prajwal.
Hi. In your previous slide about the binning, sometimes some of these packages have the option of different kinds of binning. So, for example, signal to noise binning or specified fixed binning and so on. Is that relevant for this analysis as well? And is it an option?
Yes, so you can ask for binnings in for a fixed signal to noise ratio, for a fixed time bins, etc. Again, the issue is the background subtraction technique, and depending on which technique you follow, it can vary a bit. This sort of a binning. So a priori in TV astronomy, it is already difficult to first do the binning and then decide if you have got the appropriate rejection factor. But we have tried to put in some adaptive methods which will try to give you really a 5 signal to noise ratio. I'll show some code examples and then we can come back to this point again if it's still there.
Okay, so you're saying that depending on the binning, the background subtraction technique will be different.
Yes, it's both ways actually. Depending on the background subtraction technique that you are using, your signal to noise ratio will change. And if you're using very short bins, then you will not have enough off counts to do a proper background subtraction. So not all binnings will work with not all background subtraction techniques. So this is a choice which you have to make as a user, and some of the choices which we also impose at the within GammaPy so that users don't do very wrong things.
Okay, great. Thank you.
Yeah. So the analysis package is workflow starts from the Dl3 data. Then we have which is gammapy.data, which is mainly used to read and write Dl3 data. Then we have makers, which do make the Dl4 data. Then we have what we call data sets in GammaPy, Dl4 data. And then from there, you can either go to modeling and fitting, or you can directly go to estimators. Estimators are mainly light curve estimators, flux point estimators. Of course, you can, once you have accounts, background, and excess map, you can do a proper fitting and get an excess map. Or what you can do quickly is to get the excess and divide the excess by the exposure and get the flux. And this is also one way to do a quick estimation of the of the excess that you have. So this is the typical analysis package, and then there are other packages which are standalone packages which you can use directly. For example, gammapy.irf will tell you how to manipulate IRFs. Gammapy.maps is a very flexible package which can handle any data with an arbitrary number of axes. So you have 2 spatial axes and then an energy axis, a time axis, generalized data cubes. This is being used by FermiPy, for example, to handle their cases. This is a very versatile package. Gammapy.analysis is a high-level interface which tries to condense everything into a config-driven analysis for users. Then you have gammapy.stats, which deal with various statistical methods, whether you can use cache, whether you can use WStat or other whatever tools that you can use. Then catalogs, etc., etc. And so I thought I would switch between this presentation and the Zooms and my notebooks, but it doesn't seem very easy in Zoom. So I think I have to change my analysis technique, but okay. So I will just show a few analysis examples in GammaPy. The most common examples that we would need in CTA and how to do it in GammaPy. Whatever I will show you, it is available in gammapy.docs tutorials. You can take a look there. Maybe it will help if I just show you how to access what is there on the GammaPy page, and then it will be easier. Do you see the GammaPy website now?
Yes.
Yeah.
Yes.
So this is mainly the GammaPy website, gammapy.docs.org. It tells you how to install GammaPy. You can just copy paste these lines, and this will install GammaPy, and you do a conda activate. The environment is activated. You can check your installation, and this is what you can do to download the tutorials. And then all the tutorials will be available in your computer with the data sets that we publicly release from CTA, Hens, and Ferminet. For anything that you need, you can just go to, suppose the how-to page is not very good at the moment. If you go through the how-to page and have comments, please let us know. So if you want to know some quick questions, how to access, how to check IRFs, how to do a modeling, how to do a spectral extraction, these are quick links in the how-to. Or if you want to see maybe what is, I just said, gammapy.maps are something very versatile. If you want to go to gammapy.maps, you can see all the documentation relevant to maps, etc., etc., etc. A good place to start learning GammaPy would be to go to the tutorials page. Whatever I show today will be from the tutorials. And so these are the two tutorials which will really tell you how to get started with GammaPy. And then there are some core tutorials which says how to do a Hess analysis with GammaPy, CTA analysis, how to do one-dimensional spectral fitting, flux point fitting, how to do a 3D analysis, how to do a light curve, how to do simulations, etc. And these are things which go from point A to point B. Then there are some advanced tutorials which tells you maybe more complex things like creating proper exclusion masks, what to do in case of extended sources, how to do a simultaneous fit between different instruments, more details about the modeling and fitting. Instead of you can just run a fit, but how to check the fit diagnostics, how to plot fit contours, how to look at likelihood profiles, etc. So whatever you need, you should
What
find
do you mean by 3D analysis?
Yeah, I'll come to it. I will just come to it. So again, I will go back to my screen. I don't think it was a good idea to try to shift, but please bear with me. Yeah. So as I said, background subtraction is very, very important. So first, I'll come to 1D. I'll come to the point of what is a 3D analysis. So the most common thing you would want to do at any point is to know how to do a spectral extraction, and how do you fit a 1D spectral model to a point source. So in this case, how do you do the background subtraction is you take a 1 point source, and you take off regions at a similar offset. This technique was initially developed by Whipple and Hegra, and it works when you have wobble observations. That is, the pointing observation is not centered on the source. It is centered at a specific offset from the source, and the other offset positions you take as reflected regions. So this assumes that the acceptance of the camera is azimuthally symmetric. But since you are making off regions only at a specific offset, you cannot use it to make maps. This technique works only for 1D extraction. So Prajwal, like I was saying, depending on what sort of analysis, you have to choose what sort of a background extraction. So this extraction method works only for a 1D analysis. And keep in mind that because here you are using real off measurements of counts, you have to use the WStat statistics, which I can go into details if you're interested, but this is an on-off statistic that has to be used. Again, I go back to GammaPy. Like I said, you can go to the GammaPy page, and what I do, I'll run right now is the GammaPy, sorry. Where is my, yeah, the GammaPy spectral extraction tutorial. You can run all, if you don't want to install GammaPy, you can run all tutorials in Binder in a temporary cloud server. But I will not do it right now. Right now, I will do it on my machine. I have all the tutorials which are installed here. And first, I will do a spectral analysis. So as I said, you have to use off backgrounds, and So first, this is the standard import for you import matplotlib, you import GammaPy, you import the relevant data sets that are required, and then first you load the data. And in this case, we use some Hens observations, which we were allowed to release publicly with the called the Hens data release 1. So this class called the data store in GammaPy, this is really used to access the data. So data store.get observations will get the observation IDs that you ask it to get. We already know these observations are the observations of the crab. We have these observations. So maybe if you do a print on the observations here, you will see that you have loaded 4 observations about their details, when what is the observation ID, the start and stop timing, what is the position, what is the dead time fraction, etc. Now, when you want to do a spectral extraction, as I said, you have to define an on region and some off regions. So the on region here is a target position centered on the crab. At the position of the crab in the frame, you take the, say, you see a circle sky on region, you have an on region which is selected. Then then the reflected regions will work only for, you would want to exclude the off counts only from places where you know do not expect any other source. So you have one crab source, suppose here, and then you have another source here, you would want to mask it off. So for that, you create an exclusion region and you mask it off. So here, there is a probable source nearby the crab. So this is the position of the crab. There is some probable source here. You say, okay, mask off this point position here. And then we run the data reduction change. We define the energy binning that we want to use. Then we say we call a spectrum data set maker, because in this case, we are doing only a spectral extraction. And then we run the maker chain. You also define a safe mask maker. So, okay, I'll go through the details here. You have a data set maker called the spectrum data set maker, which says whether you want to do a containment correction, what are the things that you want to be selected, counts, exposure, and energy dispersion. You do not need a point spread function because this is just a 1D extraction. You do not need a background IRF because you are extracting the background from real off counts here. The background, so then you have to say, how do you want the background to be done? You take a reflected regions background maker, which will already extract the reflected regions. And then the safe mask maker is what tells you what are the safe thresholds of your data. At which
Atri, just one thing, sorry to stop you. I think there is a question from Prajwal. She raised her hand. If I don't know if you want to take it right now or.
Yeah, sure.
Yeah.
Actually, it's about your previous thing about masking. So would that be a region that the user specifies, or can one fold in the PSF into it, or how does it do the masking?
Okay, so there are various ways to do the masks. You can say you want to mask regions with you would want to mask regions from where you expect that there are sources, or you want to mask regions where you believe that your data is not proper. So. Right. Yeah, so you can, so this safe mask maker that I'm talking about, it creates a safe mask, which will mask off regions where it thinks that the detector response is not proper. And plus you can create an exclusion mask by hand, which is really this these masks. And if you want to know more about about this mask handling, there is a tutorial on creating masks.
Okay, great, thank you.
Okay. So then you run the extraction, and then did I run this already? No. So then this does extracts the spectral region, and then you say, okay, I did it, but I want to know what my off regions look like. So here is your source, and here are the off regions centered around that source. So this is the position of the source, and these are the off regions for each run. For each run, you can see these are the off regions it has. And now you want to see, so now you have 4 data sets which have been created. You can say what is the info table, what is the information of these data sets. So you can get a quick look at the counts, at the number of background counts, at the excess, the square root of the test statistics, which is roughly equivalent to the significance at each point, then blah, 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 whatever. A lot of information is available. You can explore it. And then you can try to plot how the significance is changing with time. You can see that the excess is really increasing with time, which is an indication that there is a real source at this point. And the significance is increasing, very good. And then here is how you can write the spectrum. using an OGIP format, and you can read it back. And then, of course, you don't want to sit with this just knowing that there is a source. You want to fit the spectrum. So for fitting a spectrum, you have to define a spectral model. And in this case, you just use a power law spectral model. And in GammaPi, all fitting is done through sky models. You don't just fit a spectral model, but you fit a combination of spectral, temporal, and spatial models. Why we do it, I will explain when I come to the 3D analysis part. But anytime you fit a model, you don't fit a spectral model. You create another model, which is a sky model, which is and the other models, the spatial and the temporal models are optional, but spectral model is compulsory. Then you attach this model on each of the data sets and you do a fit. And you can see the fit quality. So you see that the fit optimized, and you can explore the fit. So you see this is your safe data range. The data outside is not safe as per the effective area standards that we imposed. This is the excess counts. This is the predicted signal counts. This is how the residuals look like. This is a quick way of accessing. The better way of accessing it would be to go through likelihood profiles, and this how to do it you can see in the modeling and fitting tutorial. Then you would want to compute flux points. For flux points, you can give a range and the number of points for which you want to compute. And to compute flux points, you use the flux point estimator, and it will take a few seconds, and then it gives you the flux points. It tells you what is the reference energy at which it fit, what is the flux, what is the what is the normalization that came out, whether the fit was true or false. So you can see here that at the last point it failed, and you can plot the likelihood profiles, and it is very clear that from these 2 points that at this point the fit failed. At the very end, you have only upper limits at these regions. This is really a fit profile. And so you were talking about binning in different. So here we started off with some energy binning because we didn't know what was a good idea. Now we see that at this energy we don't have a good statistics at this level, and we would want to combine at this stage. Either you can go back and do the entire data reduction and try to get a combined fit point at this stage. But since you have the likelihood profile, what you can simply do is combine the likelihood profiles at this stage. You don't have to do the entire data reduction, etc. By combining the likelihood profile with the appropriate statistics, you can just say, what if I combine these 2 bins, do I get a detection? So that is a nice way to directly get. Then you do a flux point fit. You see how the power law fits. So in this example, what we did is we were fitting 4 spectra simultaneously, and this gives this takes more time. What you can also do is you can stack each data set on top of the other. You can combine all the runs together instead of fitting each run together. For 4 runs, it is quick, but if you have 100 runs, you don't want to fit 100 runs simultaneously. So you can say datasets.stack, reduce, and then it will stack all of the data sets together. And then you can do a similar fitting, and then this is much quicker. As you can see, it just runs, and you can see there is some you can see that the stack and the joint analysis works similarly. The Hess crab result really is a bit higher, but that is because it has been the Hess crab result is for 14 years or 10 years of data, and here we are just having 4 data sets. So this is an example of 1D data analysis. Then we want to go to 2D analysis. So 2D analysis is, so this is how you do a spectral extraction. Now I said that you cannot use this to make maps. So if you're making maps, what you generally do traditionally in gamma ray astronomy is you take 1 point and you take 1 test region and you extract the background in a ring around that region. And for each point, you take a ring. And within this ring, you take the number of background counts and you convolve the expected background counts with this ring. So the radial dependence is corrected for, but there is no correction for the energy dependence of the acceptance. So here you can do it to make maps, but you cannot do it to get spectra. Again, you are really normalized, you are using real off counts from off regions. So this is again a WStat where the background is subtracted from the data. And again, I will go to the screen, go to my analysis, and now I will do, so here you can go to the ring background tutorial to see how to do a ring extraction. And I will do the ring background analysis in this case. So do I have time? Yeah. So again, you import whatever is required. Here we are trying to do the analysis with some, we say what is the name where the data store is required, what is the configuration for which you want to extract the observations, at which distance, etc., etc. There is a config file that is created, and you can edit the parameters of this config file accordingly. You get the data sets, you see what are the data sets that you have obtained, and then you do. So previously what we were doing by line, here we have just condensed it into analysis.get data sets. This is the job of the analysis class, and it does the data reduction for you. And then you extract the ring background. Again, you have to create an exclusion mask centered on the source. If your exclusion mask is proper, then your off significance will be proper. And in this example, we are using the Hens data of MSH 1552, which is a pulsar wind nebula, which is a very extended source. So in the ring background maker, you have to say what is the radius and the width of the ring that you want to use. Again, you make a stacked data set, and then you can see, then then you can use the excess map estimator, which gives, so this stack on-off data set is created. It says that you have total of around 40,000 counts and similar number of background counts. You have these many number of excess events, which suggests that there is some source, and you are using WStat. As I said, this is the log likelihood value. If you do a fitting, you have to keep checking this value of the test statistics to see if your fit is significant or not. And then we use an excess map estimator with a correlation radius. So you should use a correlation radius for large sources. You should use a large correlation radius, for small sources, small radius. And so you can see that there is something at the center. You have already detected MSH 1552, very nice. And to really know if your exclusion region is proper, what you do is you create a 2D histogram and of the off bins and all bins. So the off bins is the regions outside the exclusion mask, and all bins is everywhere. So ideally, you would expect a standard Gaussian with mu of over 0 and a significant and a standard deviation of 1. If there is no source in the region that you call off, and you get that, so the exclusion region is proper. And if there is something inside your exclusion region, that distribution should show strong positive excess. You do. So again, good, you have detected MSH 1552. Then we come to the question which Amit already asked, is what is a 3D analysis? And this is really, so doing 1D and 2D analysis is what was traditionally used in Cherenkov astronomy, because 3D analysis was not possible. And 3D analysis is, so classically what you would do is you would either do a 1D spectral analysis or a 2D morphological fitting. But with this, we say that no, you would make different slices of the data in this 2D morphology in different energy slices, and you fit the energy and the morphology and the timing simultaneously. So this has already been implemented by Fermi-Lat very successfully. Most of you might be familiar with it. And why do we do it? Because it takes the full multidimensional energy response into account. It can say that, okay, suppose your energy dispersion is, I mean, the PSF is small at this energy rather than this energy. This can be properly taken into account instead of assuming one PSF for the entire energy range. It is then we have shown in a different paper that it leads to a sensitivity gain for extended sources, mostly also for point light. And if you want to do separation of sources, especially for sources in the galactic plane, where you have one hard source sitting on top of a larger small source, this 3D likelihood technique lets you do that if you have overlapping sources. But I mean, while this has been very successful in Fermi-Lat, In Fermi, the background is very well modeled. You can just use a background model and do the extraction, but here you have to construct these background models, and these can be constructed either from simulations, example runway simulations, as will probably be done for CTA, or from the data, where you take all off runs and you construct the background model, say priori, which is what we do within Hens. And the reason why this is something new and has not been done before is that the control of systematics is very, very difficult. In this case, you are not using real off counts, you are using a background model. So the background model of the hadronic background is simultaneously fit to the data along with the sources. In the previous examples that we saw, when we took the model to fit to the data, we had only the model for the source. But in this case, you have to fit the source and the background simultaneously together. And so because of that, you have to use cache statistics. So for this, you can use, what are you seeing now? I can have to change my screen. This is highly irritating, but yeah. No. Sorry. Yeah. So this is this tutorial that we want to see, and in this case, so again, first we have to do the data reduction. We create the config file as per we need, and then we say what is the map on which we want to do the data reduction, what is the bin size of 0.2 degree, what is the field of view, what is the energy that binning that we want to use, because we do a simultaneous fitting in energy and spec and morphology. And then this data is extracted. So we can do the stacked analysis. First, we stack all the data together, and then we get the data. So what you have is one data set, which, yeah. So you will get all of these errors when warnings when you are running GammaPy, because it says invalid unit found in background table. Do not worry about it. This is the CTA 1DC production was a bit improper. So this is one of the errors that come out, the warnings that come out, but you need not worry. So we have
Atri, may I ask a question quickly?
Yeah.
When you define the bin size of 0.02 degree, this
Yes.
bin size is basically governed by the point spread function of your, or is it the pixel? It is governed by finally how small you can go is the pixel size.
It's the pixel.
It's a pixel.
Yeah, it is what you want to do with your, yeah. You can go to data smaller than your PSF, because you will also convolve with the PSF when you are doing the 3D.
Okay.
And the PSF will be different at different energies. So you would ideally want to go as small as possible, but then it would take forever to do the analysis.
Right. Okay.
So depending on whether you want to study extended sources or small sources, you can choose a different binning. Since you brought up the question of binning, what we do here is we see you can choose a different binning for the counts and the exposure map, exposure or the PSF or the EDISC, because the IRFs don't really change at a scale at a level of 0.01 degree or 0.1 degree. For IRF, a larger binning is usually sufficient, and a smaller binning in energy, because you would want small binnings in the true energy and big binnings in the counts. So this is customizable. If you are doing analysis, making catalogs or doing analysis with lots of data, then this is really something which you would want to change. Then you can plot the maps. So here what you can do is you can look at the maps in different energies. You can, as you can slide out, you can see that the map, how the map is changing at different energies. Plot the background map as well. You can see how the background map changes at different energies, blah, blah, blah. You can see whether how the exposure, you can do, here I'm plotting the exposure, the summed over excess, how the excess is. You can see this is the galactic center source, Sagittarius A, and some other sources nearby. You want to choose certain sources. And then what you want to do is you don't want to fit the entire thing first. You want to fit somewhere near this source, because at this point, all that you are interested in is this source. So you can choose an appropriate fit mask. Then I said that all analysis should go through a spectral and a spatial model. So in this case, you define a point spatial model and a spectral model. And the model that you fit is a combination, is a sky model, which is a combination of the spectral and the temporal model. Maybe I can show you what the model looks like. If I do a print on models, it tells you it has a name. The model name is very important. It is applied to all the data sets. When you don't give a data set name, it is applied to all the data sets. I mean, sometimes it may so happen that you have a very large data set, maybe along the galactic plane, or maybe you are trying to fit the EBL absorption for different blazars, and you are fitting 20 blazar data together. And in that case, what you would want to have is the EBL model will be applied to all the data blazars together, but for each blazar, you would have a separate spectral model. In this case, you would give the data set name for each model. That first model is applied to Mercury 421, the second model is applied to Mercury 501, and for the EBL model, it is applied to all the blazars. So this is how you apply it. And then this is, it tells you what are the parameters of the model, and then you do a fit, and then it will take a few seconds, and yeah. And you can see if you do results.success, it uses iMinui by default. So it tells you true. By default, we use the Minui fitter. You can change it. You can use SciPy fitters. You can use different backends for how to do it. There is a different tutorial on this modeling and models and fitting tutorial, which you can see how to do it. And then you can see the result. You can see the backends, methods, etc. The total stat, and how the total stat changes after adding each model is a very good method of measure of how significant each source is. It gives you the fit parameters, and then plot residuals will quickly tell you how the residuals look like. You can see we modeled this source, the residual looks okay here, and you can plot. You can look at the spectral residuals as well. This is just the spatial residual. You can do say what are the spectral parameters, what are the spatial parameters, and then you can quickly get. So in this case, we are looking at how the spectral fit is, how the spectral residuals look at in this region. You have a quick plot. You have a quick plot here. This looks well and good, but again, this is just from the excess. But what you should really do is go through a Lima estimator, the Lima method, to get a proper estimation of in using proper statistics. And for that, you can use the excess map estimator. You can say where you want it in whatever energy bins. So here I asked in 2 energy bins. You can say I want it in maybe 3 energy bins, and then it will directly give it to you in 3 energy bins. You can change the quick size. Maybe it's, yeah. So it gave you in different energy bands. It will choose the energy bands according to the energy. So okay, you can see that here it gave 1 to 2.5 TeV, whereas I asked at 3 TeV. This is because we are doing a bin analysis and my bin sizes. So if I give 3, it will choose the bin edge nearest to 3 because the data is already binned. And then you can look at the full significance, and you can see that in this case, I said, if you look at the distribution of the histograms, it should come out close to 0 with a sigma of 1. It is not the case, which is not surprising because you can see that there are other sources and the emission from the galactic plane, which is not modeled. So this I did for one data set where everything was stacked together. You can do a joint fitting as well. I'm not going to do it at this point because there are other examples that we can see. So, yeah. So then there is another tutorial on CTA data analysis. This you can see, but I think everybody is tired at the end of the day, and I can, of course, I can keep talking for ages, but I don't want to put everyone to sleep. Then there's the question of making light curves, which is very, very common. For light curves, you can either take, I think, do light curves for observation bin, or you can take light curves for very, very small times. I mean, for light curves, either you can want to make GRB light curves, which would be maybe bin for a few seconds or few minutes, or you might want to make laser light curves averaged over a week or 10 days or months. And the background reduction in these two cases is very different, because if you are using data averaged over months, then you have to combine different runs together. And when you're combining different runs together, you are combining runs taken at widely different conditions with different responses. So you have to be very careful how you stack them together and how you do the background extraction at that after stacking. On the other hand, if you're taking, but the statistics is fine, you have enough background also to do the fitting on. On the other hand, if you are doing a light curve on a very small time scale, maybe for a flare, where you are taking for the PKS 2155 flare, maybe you are taking 2-minute light curves. In this case, what you have to be very careful about is the fact that because you are taking data in 2-minute bins, you might not have enough off counts to normalize the data on. So in that case, another thing that might be is that when you are making a light curve, what you always assume is that each point in the light curve is independent of another one. But if you have a 30-minute light, so because you don't have enough off counts to normalize the data in a 2-minute interval, what we do within GammaPy is we have to take one run with one IRF, and we say, okay, the background doesn't change over 30 minutes. We normalize the background on the entire 30-minute data set, and we take 2-minute binnings from that. But in that case, the assumption that each data set is that each point in the light curve is independent of another is not totally true, because there is some correlation, bin-to-bin correlation, which we are introducing. And this, we try to keep this into account within GammaPy, but and that's why there are two different light curve tutorials for the light curve flare and light curve normal.
So I think Prajwal again raised her hand. So if you would want to take the question.
I was just wondering, so where the 3D can be such that the third dimension is either energy or time?
Yes, the one energy dimension has to be there. If you want to do a 2D fitting, you have one bin in energy, and yes, you can also have in time. So in the light curve, I think it's better that I show, but I will not go through the entire code example, but maybe I will. Yeah. So if I open the light curve simulation. So this so here what we do really is we in the model we have a spectral model and a temporal model together. So what you can really do is instead, so either so this is what you get after doing a normal light curve extraction. You have time and you have flux and you have upper limits, etc. And you might want to fit a decaying profile to it, whatever. But what you can also do is fit all of them together using a temporal and a spectral model combination. So what you end up getting is one model which has time and spectra together. So this is really something which happens together. And if you really want to see whether your maybe for blazars, you want to see whether the spectral index is changing during a flare. This is what you can do in this way. You can fit the spectra and the flare profile simultaneously. If you want to see whether the spectral profile is different between a flare state and a quiescent state, you can attach two different spectral models and the same temporal model.
Okay, thank you.
Yeah. And then there is the question of doing simulations. And this is probably the most useful case at present because you don't have CTA data and when doing simulations, there are two ways. One is event sampling, where you simulate a complete event list, which will give you both gamma-like events, which will give you both the Monte Carlo, you do a full Monte Carlo and you simulate an observation. It is very realistic, but this is more time consuming. And then the other thing is when you simulate a reduced data set. And this is, if you're familiar with expect, this is what Fake-It does in expect. You simulate just the counts and the background spectrum. And unless you, I mean, this really suffices for most cases. For most analysis, doing a full event sampling is not necessary. Doing a bin simulation, which is much faster, usually does the job, because this is what you get after the data reduction stage, and it's fine. So for this, we have we have more than that actually. We also have a light curve simulation, which I was just showing, and we have a spectrum simulation. We have how to do a 1D simulation, how to do a 3D simulation. This is for the bin simulations, and how to do an unbinned simulation, which is really an event sampling tutorial. So maybe I can show one of them at least. Or I'll just go to, I'll not run the codes again at this point because it's a bit late. So just to do a spectrum simulation, what you will do is you define a spectrum, the lifetime and the pointing direction for which you want to do. You look at the on region, you define the spectral model, and then you load the IRFs, the instrument response using which you want to do the simulations. And then you do a data set you create an empty data set with all the IRFs. Of course, so in the maker, you have to say that you create the exposure, energy dispersion, and the background. You need not create it because there are no counts at this stage. You just have loaded IRFs, and then you do a data set.fake. And when you do a data set.fake, it generates fake counts, and you have your simulation, which is done. Then you can do a 3D simulation, in which case you give not just a spectral model, you give the geometry on which you want to do the simulation, and the energy bindings, and the spatial and the spectral models with which you want to do the fitting. And if you want to do a full event sampling, then it is a bit more complex. Then you have to define an observation. You have to create a fake observation in which you will put in the simulated event list. You have to start from a map data set, because that is basically data sets is basically our go-to function. And then again, you have to define the observation conditions and the model of the source. And then you do a full event sampling. You use the event sampler, and from that you do a full event sampling, and it will give you source with Monte Carlo ID1, and it will give you background with Monte Carlo ID0, and then it will really give you how the events look like. It will give you a simulated events data set, and then there is, of course, you simulate an observation. There is the intricacy of how you write it to the file, what are the appropriate headers that you get, etc., etc. I can talk more about this, but if it's interesting. You're seeing my presentation again, I hope. I assume so.
Yes.
So this is basically it. So if you have any questions, then you can contact us on GammaPi Slack. And this is quick questions, immediate help. There is a help channel, there is the dev channel, there's the general channel. You can please do ask questions. We try to be as swift as possible. If you have more serious questions, you use GammaPi and you find a bug, you want another model introduced, you think this is not good, then we are all open source, open development on GitHub. So you can contact us on GitHub. If you want to contribute to GammaPi, then this is a very good place to start. If you find an issue, you can say that this is what I don't like about GammaPi, and say this is how it can be improved. And if you're willing to say, you can say, I can put in a PR, you can put it, then somebody from the dev team will, you can put in, you can say, and then they'll say, yes, you can go ahead, or this is the reason why we don't want it. And then you will put in a PR, and somebody will do a code review, and it goes in. So if you are interested in contributing, or you don't have to be a regular contributor. If you can be a one-off contributor, you can put in one piece of code if you think that's bad in GammaPi, whatever. Then there is the GammaPi mailing list in Google. We use it less often than Slack because Slack is quicker, but you can also send an email to the mailing lists. We do regular GammaPi calls announced on the CTA mailing list. We have now also started doing non-CTA GammaPi calls as well. We have regular dev calls. And this is from the last time we could all meet personally. After that, all the sprint weeks have been online. So thank you. And I can take questions. If you want an in-depth discussion of something else, we can go into that.
Okay. Thank you, Atri, for a very nice presentation and also pretty detailed, giving an overview of analysis using gamma pi, giving some demonstrations also. Thanks very much. So it's time for a few questions. Yes, Professor Acharya, yes, please.
Yeah, hi, Atri. This in this gamma pi, the analysis for the pulsar is also included, or I missed that part?
So yes, there is some pulse analysis. It is not very well developed, I must admit. There is some functionality. I will again new share. I will go to the, if I can find it. So there is and so on the extra topics there is pulsar analysis with gamma pi, and this tells you how to do pulsed analysis. So how to make phasograms, how to do angular cuts, how to do phase resolved map. I think this can be very well improved, the pulsar analysis. It's just that none of us did it yet. If there is any interest, you can request us and we can do it.
Yeah, okay. Another question is, while you are mentioning the masking some regions to the source, how many regions can be masked? What is the upper limit?
No, there is no upper limit. So you can make as complicated masks as you want. So in this example of creating exclusion masks, you can you can create an list of exclusion regions. So here you are masking one circular region and one square region. Maybe you have broken pixels in this region or whatever. You mask this. You can mask from a catalog of sources. You can and then you have two independent masks, and you can combine these two masks. If you see, you can create the masks from statistically significant pixels. You could say that anything above 5 sigma you mask off, and you end up with bizarre masks. It's
okay. Yeah. Thank you.
Okay, so there is a question from Balchandra, please.
Yeah, Atri, a very nice presentation on the analysis by using gamma pi and so on. It looks very interesting. I had a follow-up question to Professor Acharya's question. So you mentioned this pulsar analysis. So for the timing part, are you using standard ephemeris from Tempo, or what kind?
We are using Pint at this point.
You're using Pint, okay.
Yeah.
I may just say that Pint is not so extensively used, although I think it's Python based, and that's probably one of the reasons why you are using it. There is a Python interface of Tempo, and Tempo is the de facto pulsar timing package as far as pulsar timing is concerned. So so there is a Lips Tempo which you could actually import inside the Python interface and connect to that. It would be better to sort of use the tool which is used much more widely compared to Pint. Although Pint is also equally good, but it's not so widely used by the community.
Okay.
So that try and use Tempo as far as possible.
I mean, the issue is none of the lead developers in gamma pi are pulsar experts. So
okay.
it's a personal bias, and pulsar analysis has been done as per the requests that we get. So if
I can help you guys in case you put me in touch with whoever is doing the pulsar part.
That would be fantastic. So if you really want,
I can help, because timing is something which is very bread and butter for radio astronomers. So it's not a big issue for us to help you out.
So that would really be fantastic. We can get in touch. Thank you so much.
Sure. Thanks.
Thank you.
Okay. Any more questions? I don't see any at this point. So yeah,
Yeah. So Atray, you have showed that we can simultaneously fit data from different telescopes like Hess and Fermi. So I have a two question, or else basically a one question. The first thing is both should have the DL3 kind of data thing, but how we deal with the systematics of the instruments in your experiment, because both may have a different systematics.
There is actually a paper on this already, joint modeling fitting, which is called the joint crab paper. So there is the first author is Cosimo Negro. I'm also one of the authors. And there the aim was really to show how to do direct fitting from different data sets and how to take systematics into account. For that, we modified the likelihood a bit and added priors on each instrument. So if you see this paper, this is a paper on the joint crab fitting, and this notebook really tells you how the systematics were handled. If it loads, yeah. So we added a shift in the energy scale, and yeah, oh, no, sorry, we don't have the nice plots on the public tutorial, I think. Yeah, you can look at this joint crab paper. Yeah. That tells you how to do the how I mean, taking care of systematics is a personal choice, of course. So you have to put the prior in the likelihood accordingly, and because you're fitting the background for each data set separately, that already takes care of some of the systematic involved of a lot of it, because you have a different background model associated with each data set.
Okay, thank you.
Atray, just to quickly ask the follow-up on what Amit was asking on the systematics. So when you introduce the systematics of shifting the energy scale by a certain percentage, are you doing it absolutely at the level of Monte Carlo, or are you doing it at a much later level, let's say during Hillas parametrization?
No. So as I said, the science user has no access to the Hillas parametrization, has no access to Monte Carlo. So what he has access to is only gamma-like events and the associated IRFs. So the way to do a joint fitting of different data sets is you do the data extraction, you extract the counts, background, you extract the cubes for each data set separately. You have one thing for Fermi, one for Hess, one for CTA. Then you have a different background model for each, and when you're doing the likelihood fitting, you're doing a joint likelihood across all three. And in the joint likelihood, there the likelihood is not just the standard cache likelihood, which is I mean just the normal Poissonian likelihood, but there you introduce a factor along the a prior along of the other data set along a shift in the energy scale. This really goes in the final likelihood winning.
I see. Okay. Okay, thanks. So are there any more questions? I don't see any more hands raised here. So, okay. So if there are no more questions, let's thank Atray again for her very nice presentation. And let me thank all the speakers of this session for their presentations. And I hand over the mic back to Amit for his concluding remarks.
Thank you, Pratikda, for chairing the session, and Stefan as well as Atray for a wonderful talk. We have learned a lot about the computing, about CTA and the analysis part, and I have even learned so many things in last 15-20 minutes. So I believe today we have learned a lot about the very high energy gamma ray sources, the technique by which very high energy gamma rays can be detected, as well as we also learn about the upcoming telescope, Cherenkov telescope array, and the timelines and the difficulties and the challenges which are involved with the CTA telescope. So I believe today is a very fruitful day for all of us, and mostly for the students who can learn a lot from such workshops. So I request all of the participants and mostly the students, in case if they have any thing which they like to discuss to any one of us, please write to us, please contact us. Especially if you do not have any emails addresses, you can contact me, and I will try to forward them to the concerned faculties or concerned speakers and try to get your answers. You can also use Slack channel, which will be open for some time, to discuss the any part which you have missed or which you like to like some more discussion. So with this, I would say that we have reached to the end of our workshop, and it's a very fruitful day where we have learned a lot. And finally, I like to thank a lot of people who have given the opportunity and made this particular workshop happen finally. So I start with the ASI team, who has actually given the opportunity to us to conduct this workshop, organize this workshop. So I like to thank the chairperson of Astronomical Society of India, Professor Anupama, and the SOC and SOC chair, Professor Oja, SOC secretary, and ASI secretary, as well as the VOC members who have helped us to actually conduct this online workshop without any hurdles. So we have a very smooth day. Most of us or any of us did not suffer any internet related issue. However, there will be a small glitches, but more or less it has gone fine. Further, I like to thank our panelists who have contributed and showed a roadmap to us for the future multi-wave band and TO related concerns. And we believe we will work out a roadmap and try to make an informal consortium slowly, and maybe it could be formalized at some point. And now I would like to thank the chairs of all the sessions, Professor Prabhu, Professor Acharya, Professor Alok, and Professor Pratik Majumdar for their time, and all these speakers who have given a wonderful talk and taught us a very interesting aspects of gamma ray astronomy. And finally, I like to thank all the participants who have kept very patient and listen all the talks, and hopefully they have learned. We have all learned a lot. I understand these kind of workshops are quite heavy when you have to sit continuously for a day in front of a computer and just listen. I would love to host such workshop in person as soon as it is possible for us, and hopefully within a year or so, and hopefully we'll come back with in-person workshop or a school. I also like to thank the directors of ARIES, IIA, IUCA, NCRA, and RRI for taking interest in our panel discussion and appointing and nominating several senior scientists who have shown a very great interest in the project. I also like to thank the advisory committee of CTA India Consortium for giving us suggestions and showing the roadmap, how we proceed towards this workshop and make it success. And finally, I like to thank the VOC and ASI and IUCA, ARIES, SINP, TIFR, and IIT Indore for all support which has been given by these institute. And I like to thank Professor Pratik Majumdar, Professor Varsha Chitnis, Professor Ranjiv Mishra, Professor Manas Maiti, Professor Meenakshi Gupta, and Dr. Debanjan Bose for helping me to make this particular workshop happen. Thank you very much. With this concluding remarks, I would say the workshop is closed. Thank you very much.
And thanks a lot to you, Amit, for doing all the hard work. I mean, so you are the main workforce here, doing everything. So it's a very, very big thanks goes out to you. Yeah. So, and I
Thank
hope, yes, we will meet soon face to face for such kind of workshops in future, very near future, hopefully. Yeah. Thank you very much, all.
Have a nice day. Have a nice evening.
Yeah.
Bye.
Thank you and bye-bye. Yeah.
Be safe.
Thanks. Bye.
Bye, Atreyu. Very nice talk.
Thank
Maybe
you.
we can, if you have time, maybe we can just chat sometime in coming weeks.
Yeah, sure. Well, I'm in India right now, so it's not a problem.
Sure, I will give you a call.
Sure. Thank you.
Take care. Bye. Bye, Professor Acharya.
Bye.